Hey everyone, and welcome to the SaaS developer community where we learn from each other how to build software as a service. And with me today, I have an old colleague and really impressive expert in building really deep software infrastructure as a service, Eno Thereska. And he pinged me, I think maybe 2 months back, and said, yeah, I have some ideas to share about cell-based architecture. And I was like, oh, this is fantastic. Everyone keeps telling me that they hear about it, but not enough people actually talk about it. So I'm super excited to have you here, I know.
Thank you. Thank you so much, Gwen. Real pleasure.
Yeah, and I think without further ado, I can just let you jump into explaining cell-based architecture for us all.
Yeah, I will. Thank you. You can see my slides, okay?
Now we can.
Good. Hey, super great being here. I'll talk a little bit about a subject which I think is a little bit under-discussed when we talk about building SaaS services and control planes and all that. And that's the subject of cell-based architectures. Couple of words about me, a couple of relevant bits to this talk. I'm currently helping Alcion build their control plane. Alcion is a startup in the data protection and ransomware detection and protection space. I'm helping them build the control plane. So I'll talk a little bit here about what we're doing there. Yeah, and most recently, I was also a principal engineer in Amazon before Alcion. And I saw there a broad range of services across machine learning, streaming services, and storage, and helped build a couple of services, all cellularized. So I want to share a couple of the learnings that I saw there and have a discussion about this and see how this cellular service can actually help you build a robust SaaS service. Now, we're all building on the shoulder of giants, and there have been a whole bunch of talks, a whole bunch of really great talks as part of this series that Gwen is running. And I want to start where they have left off. We have talked about the importance. We're going to take this for granted. We've talked about the importance of decoupling the control planes and data planes. We know that's important because we want to isolate them from one another. The data plane should continue to work even if there is something wrong with the control plane. That's great. We have talked about the use of availability zones or zones in general. These are data centers or a collection of data centers that are physically isolated from one another. So if something goes wrong, there's flooding in one of them, the other ones are still up, and your tasks can still be available. Okay. Now, both of these are high availability building blocks. And this talk is going to be mostly about availability. There's going to be a bit about security as well and isolation, but it's mostly about availability. So then the question is, are these two building blocks enough? And it turns out they kind of aren't, especially if you want to build a highly critical service. So let's look at a couple of real examples that I've seen, and I'm sure you have seen as well in production when things go wrong. The first one, here we are trying to do a deployment and something is misconfigured. We've done the deployment with the pipeline is going to prod, and then the entire control plane is affected and the system is down. You can always roll back. Okay, but now you have an availability issue because you have to take the time into account and something went wrong that affected all your customers on the control plane. The second one is a little bit more mundane, but it's also, it happens all the time. You have reached some sort of quota. You have built your control plane. If this was 2018, you have probably built it with VMs, and later on with containers, and more recently perhaps with the serverless components. But somehow you have reached some quota, and you forgot about it. That quota is now reached. You can't onboard new customers. Again, an availability problem. You can't accept new requests until you do something there, right? And the third one is a little bit similar to the first one, but this is more about buggy code. you've deployed a buggy feature, you'd love to test it with a few customers, but you have kind of deployed it to your control plane and all the customers are affected. Now, for these particular problems, it doesn't matter if things were in different availability zones. It doesn't matter that you have decoupled the control from data plane. You still have to deal with them. And all of these are going to lead into unavailability, which is not really great. So if we want to build robust applications, a little bit more robust, now I'll talk a little bit later. Do you really need this? When do you need this? So this is not all the time, okay? But if we want to take things a little bit to the next level, we're going to talk today about cellularizing the control plane and cell-based architectures as a key to making the control plane more robust. And now the overarching theme is going to be, cells were typically used for critical services, but are now achievable for most services with a little bit of effort. So you too can also use them for your system. Super high level picture, okay? So what are these cells? How are things going to look like? And here is the control plane and the data plane. I'll talk about some examples, right? The control plane could have your databases that keep the tenant information, metadata. The data plane could be something that moves the bytes around, right? But things are going to look a little bit like this. So we have taken the control plane, the customer requests come there, right? And instead of just sending this request to one control plane, we're going to break up this control plane into a whole bunch of things called cells. And we can also break up the data plane. That's going to be interesting, sometimes not necessary. I'll give some examples later. But for now, we focus on the control plane. And once we break it up, we're going to have, we're going to have a routing problem. How do we choose the right cell? But all of a sudden, we also have something really great, which is if something goes wrong with one of the cells, the other ones can continue to work. And they're all completely isolated and independent from one another, which is good. So what do cells give us? So they give us better isolation, one, across tenants, but two, also just prevent us from, they kind of isolate our own buggy code in a sense from touching the entire control plane. They give us an opportunity to do an even better deployment of software. We're going to see how we deploy from cell to cell and then roll back if something goes wrong. They also give us this extra benefit. We can rapidly scale the infrastructure. We can easily, start a cell in any region of the world in just a couple of hours, maybe a day or two. And that's a great way to scale our infrastructure and onboard new customers without worrying about quotas. Okay. So again, this theme, one of the main messages of this talk is these were used in the past for critical services. I'll talk a little bit. I have a pointer later on to the Fargate service, for example, in AWS, or Lambda or DynamoDB. But today, anyone can really use cells with a little bit of effort, as we'll show here. Okay, so hopefully that gave you an idea of the motivation. Again, we want to build robust services. So let's talk a little bit. Let's get a little bit into the details. And then we're going to come out of the details again and do a case study with Alcion's control plane. But let's get a little bit into the details. So what exactly is a cell? So here's the theoretical part, and then I'll give a little bit of a sneak peek. So a cell is, however you can get into the completely self-contained and isolated part of the control plane. And it's something that's going to be sufficient. It's like it provides like life support for n% of the customers. So maybe 1% of the customers. Maybe, if you want like an absolute number, maybe 100 customers. Okay, not more than that though. There is like an upper limit. Yeah, and the cells do not communicate with each other. There is no event bus. There is nothing of that form. Right, the cells just are able to completely service the customer requests and provide what's needed. Now, I want to give a sneak peek so this doesn't get super theoretical. So for Alcion, a cell is physically implemented simply through just another AWS account. So we run Alcion on behalf of the customer. The customer doesn't need to run anything, but we have a lot of accounts in the backend. There are other ways to do this, that you could have a cell through VPCs and things like that, but we do it through an AWS account where one account is one cell. Okay. Now, what do we have in the cell? Viewers of this series know what goes on in the control plane and are not going to be surprised if we see that in this cell in the control plane we have compute. Okay, this can be lambdas, this can be for whatever service provider, this can be VMs. Okay, there's going to be monitoring there to see how and logs, right? There's going to be a database that keeps the metadata about tenants and things like that. There's probably going to be an event bus and it's going to be storage as well. Now, we all know just because I've shown storage on the control plane doesn't mean that this is a data plane. This is still part of the control plane. It's just the control plane needs to maintain a lot of state as well to kind of run the data plane, right? Sometimes the state can be petabytes in size, and this is just metadata. So a cell is just going to contain this ecosystem as well. It's going to contain a little bit of all of these things, sufficient to run the workload that the customer demands. Okay. Now, when do you start a new cell? Let's look at a couple of answers. So one answer is going to be here, and this is kind of like the obvious one, but also a very common one. You start a new cell whenever you have reached some quota, and you cannot onboard new customers. So this has changed a little bit over the years. So I remember, like in the my pre-serverless world, 2018. The things you would want to monitor here to see if you've reached a quota are things like how many VMs are you using? Are there any IP limits? Are there any actually, I've almost forgotten about all of those because I've moved to serverless now and I've forgotten about all of those limits. Yeah, but I remember there were a whole bunch of them, right? Now, today there are still limits in some of the services, no matter from what provider you use. So these hard limits have mostly gone. You can always ask for a quota increase, okay? But there are still some hidden limits and you need to look at it carefully. So for example, how many concurrent lambdas can you start? It cannot be infinite. How many containers can you actually start per minute? You can have, in many services, you can have an unbounded number of containers you start nowadays, but the number you can start per minute is actually there are still hard bounds there. Okay,
I think AWS also has a limit on the number of roles you can have, like in terms of like the
yes,
role
absolutely,
definition.
absolutely.
And we ran into it surprisingly early in the life of a control plane. So yeah,
and it's always a moving target. There is always every year these limits kind of get pushed further. And I look forward to a world with no limits, but they still exist there. So this might be a boring reason to start a cell, but it's a very valid one where you just reach one of these.
And this actually
quotas.
talks to the way you are mapping cell to an account, because when we talk to AWS and say, hey, we just ran out of a number of roles we can have, they went to us and said, well, you should use another account. So this is a really good mapping.
Yes. Now, another reason is you want to also have a very rapid unit of deployment. So Alcion can deploy in a new region, which is part of a region build, really quickly. We have this goal to deploy within 2 days. And I think that's going to be decreased even further over time. And the deployment itself happens through well-known tools like CDK or CloudFormation or Terraform. But the fact that you have built your control plane in cells and you can just simply add cells and then the right thing happens really helps with the story of deploying quickly in a different region as well. And that's helped us deploy in Sydney, for example, quite quickly. Okay. Now, the other reasons are also there. So, like a real limit, a real reason here you want to have cells is to limit the blast radius, right? When I say real, I meant like maybe a little bit more exciting than just quotas, right? So you pick the number of customers to support per cell, for example, 100. And this is hard. This part is hard because it feels like you're limiting yourself. You're saying, oh no, I'm going to only support 100 customers. That's a bad thing, right? But it turns out that the cost of opening new cells is trending towards $0. It's not exactly zero yet. I'll give some examples, but it's getting very cheap to open a new cell. So it's okay if you support if you decide you're only going to support 100 customers per cell. If you don't feel comfortable with having more or less customers per cell, it's okay to say 100 and then just start some new cells. the cost of doing so is pretty low. And again, like the reason here to start a new cell is to limit the blast rate. If something goes wrong, you only want 100 customers to be affected, not all of your other thousands of customers. Okay. Now, how are we going to open the cells? A little bit about that. So there are many ways and hybrids of these ways, but like two kind of standard ones are: you open up a cell, you fill it up with customers, you kind of monitor some quota that you might be reaching, and then you say, oh, we're almost there, we're 80% there. You get ready, you open a new cell, and then you kind of seal the old cell. You say, we're not going to accept any more customers there, which again sounds bad, but it's not really, because it's kind of free to open up cells, more or less, right? And the other way is to do like a round robin. You say, I'm going to have 10 cells, and then you round robin customers across them. In practice, you'll need a hybrid of this, because with the round robin one, well, you don't really know how many customers you're going to have. So you can start with 10 cells, but then you might end up with 30 cells. So you'll need, and one of them might be really full. So you'll need like a hybrid of both of these two. Okay. Now, how do you do routing to the cells? Now, there are some kind of theoretically easy ways. You do like a so the problem here now is like you have these 30 cells on the control plane. A new customer comes on board. Where do you send them? And in the future, when this customer comes back again, how do you route their request to the right cell? And there are kind of like the standard. You can do a mod on something like a hash of the tenant ID, something like that. You can make it load based. If some of the cells are more loaded than the others, you can go to the other ones. You can have some deterministic or more complex routing logic there. This turned out to be quite. It's not. I'll show Alcion's version. It's not always easy to implement this routing, especially because for us, like DNS-based routing doesn't work. We don't have like. We can't just go. A customer cannot just go to any cell. They have to like go to. Once they go to one cell, they have to keep going there. And because we're fully serverless, even our router is serverless, which is going to be interesting. So I'll talk a little bit about that in a later slide. Just as a sneak peek, though, that the routing is going to be a little bit of work. It's not going to. You might not find something off the shelf immediately there. And then how do you do the deployment, which is also going to be important for again robust deployment of software. So in case something goes wrong, right? You have a way to pull back. Typically, the deployment is done in this thing called waves, which is a set of cells. And here I'm showing, I've labeled the cells in 3 waves. There's wave 1, 2, and 3. And basically, the idea is that you deploy on one of the sets, you monitor the metrics, you have some bake time in there, maybe even a couple of hours. Yeah. And the first thing you do if something goes wrong is you roll back. Never roll forward, always roll back. And if things go well, though, you just move to the new wave. Okay. You can also do it cell by cell. Now, if you have a lot of cells, that's going to mean there is this trade-off that your software is going to take a while to be deployed throughout the entire system. Later on, I have a slide about this thing called a tiny cell, which can be really useful for testing software, like where you can just point just like 1% of your customers on or even one customer on a very small cell and kind of get started from there. Okay. And across regions, you can choose to do the wave. So whenever we deploy, for example, we go, US East and US in parallel. You can also serialize it. Here, I don't have like a super strong opinion. I've seen teams do either of those. Again, if you are in a lot of regions in the world, probably parallelizing it and going cell 1 on all of the regions makes more sense, because you're going to deploy the software faster while still maintaining the level of robustness you desire. So, main takeaways so far, and what are some of the things that you'll need to do if you're thinking about cells? The first one is monitor quotas. You are likely already doing this. I'm not telling you anything new. You're probably going to have to build the thin routing layer on top of your control plane. And jumping straight to number 5, probably you're going to have to avoid the need for global state. There's going to be a little bit of global state. We'll see that. But these two, number 2 and 5, are a little bit more effort than the other ones, which you're probably already doing. Okay. And then number 3, you're going to deploy cell by cell or in waves, and then always roll back if something goes wrong. And of course, number 4, just ensure the rollbacks work well. Again, you're likely already ensuring that as part of your deployment strategy. We'll talk more about 2 and 5 soon, but these are the main takeaways so far. Let's look a little bit at Alcion's control plane, a little bit of a plug about Alcion, just so that you get a little bit of context. We protect your data from ransomware and malware and outages, and we also back it up and allow you to restore it. The architecture itself, so that the rest of the discussion makes sense, the architecture is completely serverless. Just as a side note, I seem to have bypassed I started with VMs and I've gone straight to serverless, and I only had a little bit of Kubernetes in the middle. So if you guys have questions about Kubernetes, I'm probably going to be weaker there, but we have jumped straight to serverless, and this has allowed us to deploy really quickly. Now we have a pragmatic mixture of event-driven, so microservices, but also state machines parts in there, and these state machines are really performing a lot of functions, and either the entire thing completes or it doesn't, but they do it all in one go. Yeah. So I think we're not. I think we have a little bit of everything in there. So it's. I think it's pretty pragmatic.
So
We have.
something
Yeah.
that surprised me here, you almost make it sound like event-driven and state machine-based architectures are opposites, and you kind of ended up being pragmatics and mixing them. But I always thought it's two patterns that actually go together extremely well.
No, you're right. You're right. Maybe I got too defensive there. I'm not sure why. I guess depending. I think this audience absolutely appreciates that it doesn't. They are kind of like sides of the same coin. An event gets started, gets intercepted. It might start the entire state machine, which itself will send events further downstream. You're absolutely right. I didn't have to make it sound like they are completely different things. They are sides of the same coin. Absolutely. The data plane is open source, and we engage with the community to develop that. It's called Corso. And the data plane deals with a whole bunch of interesting things around movement of data, just the actual flow of the bytes whenever you're doing a backup. And it has a whole bunch of really neat things around deduplication and encryption and verifying that the data is correctly moving and so on and so forth. But the control plane manages those data flows on behalf of the customers. Okay, and it chooses when do you back up the data, how do you restore it, and it also detects. It does some analysis on the data, it detects ransomware, and it flags it to the customer. So that's what the control plane does. Okay, so here's a picture of that, and I have now labeled some of the previously we had some boxes with things like compute, and here I'm making it a little bit more concrete. So here we see first the true separation of the control and data planes, where the control plane sends messages to the data plane, but only receives back metrics and logs. So in case the data plane is compromised, that doesn't touch the control plane. What is in the control plane? We use Lambda quite heavily, and step functions, DynamoDB, for storing the metadata. I'll talk a little bit about how much metadata is in the control plane. And then on the data plane, we run Fargate, which is AWS's container service. And there, as the final thing that runs there is Corso, which is the open source product that actually moves the bytes from the source to us, to Alcion, that performs the actual backup and the analysis of the data. Okay, so what exactly then in this world is a cell again? So a cell is an AWS account. The cost of opening this new cell tends to be zero, but it's not exactly zero yet, unfortunately. There are some services which are not fully, their cost doesn't go to zero when they're unused. I'm pointing fingers at the search service right now, but there are others as well. Aurora V2 is still not zero cost if you don't use it. I hope in the next couple of months or years, this service is also, their cost goes to zero if you don't use it. Because if they do, then really, truly, the cost of opening a new cell is zero. Okay. Right now, again, it's not zero because, for example, the search service has a baseline cost. I think it's something like $700, probably, even if you don't do anything at all, right? So this kind of answers this question, which is a little bit below, which is why if the costs are low, why don't you just do one customer per cell? Which I think is a valid question. But unfortunately, they're not quite zero. And even if there were zero, so we have we support around 300 to 400 customers per cell. That number comes, if we want to get into the details, it comes from the rate of starting containers per minute. That's our main limiting factor. Even if the cost would be zero, probably one customer per cell might be a bit of an overkill because, well, I don't know. Could it just work out? We do have this notion of a tiny cell where we could really put one customer per cell, but with many customers, maybe I'm missing some sort of like a hidden cost. Maybe there is something I need to look into AWS's organizational service if there is like a per account. I mean, certainly it's a bit of a pain to like just open those accounts, but even that can be automated. So I don't know. I'm debating this with myself now.
I'm thinking you mentioned one other benefit of cells, which is around orchestrating upgrades.
Yes.
And you do want to orchestrate upgrades in groups.
Yes.
And I can imagine a world where you say upgrade a cell and then you have like a cell level automation that is well tested. And then the layer above that is not necessarily optimized to upgrade thousands of cells because it seems a bit hard to manage. So
it's always
the
that extra
layer
metadata.
hierarchy seems useful.
You're absolutely right. There's always a little bit of that metadata overhead, right? If you make the cells too small, then all of a sudden you have a lot more of them, and then something is going to cost you later on. And you're absolutely right. The deployment is going to start being an issue. Like all of a sudden your pipeline now is going. How are you going to even organize your pipeline, right? If you have like 1,000 customers, you're going to have 1,000 stages.
Do you get if you aggregate monitors like metrics on a cell level, and then you have like a view of cells that you can drill down into like bed cells versus getting all the metrics into one place, which is obviously humongous.
No, that's good. Yeah. I needed this discussion because I've been thinking about this. How low can we go? How many customers per cell? But that's right. There is a cost. So it might be that the cost of opening a new cell is zero or close to zero in terms of just opening the account, but there is all this other cost of deploying and monitoring and thousands or tens of thousands of cells. So yeah, in practice, 300 to 400 customers works well for us, and this one customer per cell remains kind of like a theoretical data point. And we also have this goal of bringing up a new cell in 2 days, and there is no reason why you can't bring it up even earlier. Sometimes, depending on the technology used for the actual deployment, CloudFormation or Terraform, that might become like the bottleneck in the end, not so much like the creation of the cell. Sometimes, when you know the quotas for a cell, kind of like a boring bottleneck might also be that you have to ask the cloud provider to give you that quota. So whenever we open the cells, I know we're adjusting some of the quotas because the defaults are not good enough. So just sending just asking for the quota upgrade could take a couple of hours, 24 hours or more. What are the quotas we monitor? Two of them, which are again not like the obvious ones: the number of concurrent Lambda executions and the containers startups per minute. I think there's a hard limit of 500 containers starting up per minute. So that's
exactly that.
Yeah, it's kind of like it's hidden in there, right? And it can hit you if you're not ready for it. But yeah, I'm glad these are new things we monitor. In the past, it was things like elastic IP addresses and things like that. I'm glad we don't monitor those anymore. But as you said, we might want to monitor other things as well, like security policies.
And look at all the things that without serverless you would have been monitoring, and now you don't. You are not
Yes.
monitoring CPU. You are
Oh
not
no, disk
monitoring how much
size.
disk space you have left. Like there's just so much stuff you don't think about.
Absolutely. Disk size. I really never ever want to monitor disk size again.
I
Ever.
know.
Like it should just be there. Absolutely. Really great point. Now the routing. For the routing, this is very specific to our service. Our service is such, and I perhaps should have mentioned that in the context, is that in our service, the customer tends to onboard and tends to kind of start auto protection. The customer might have hundreds or thousands of users. They all need to be backed up, and we need to detect ransomware and things like that. But the customer doesn't, by default, doesn't interact, say, like in a real time, doesn't need to interact, get any bytes in real time, because we take care of all of that. Okay, so because the interactions with the customers allow us, in a sense, a little bit more leeway. We don't need to, it's not like the customer is getting these bytes. As I said, they are just sending us things like, hey, protect this other user, or hey, can I get a list of all the actions, all the backups you did during the last couple of days? We have a little bit of leeway there. So our routing is based on a combination of API gateway and these cross-account lambdas. So a lambda actually does the routing. We need to go to a particular cell. It goes to a lambda itself, which might be a bit weird, right? Because lambda is a compute unit. But we found it easy to use it to kind of point it to any other cell that we have and kind of translate the requests from when they come to the API gateway to the cell account as such. DNS-based solutions do not work in our case. They can't quite express what we need in terms of routing logic. They might work in many other cases. But yeah, that's our we have a
Right.
lambda-based
I
routing.
need to drill into how do you avoid, because if you have multi-region, you probably want clients to talk to a nearby cell, and
Yeah,
that's where DNS usually shows up as a good idea.
yeah, you're right. You're right. So this kind of this doesn't talk about that layer. This talks about once because in a region, even within a region, we can have tens of cells.
Mm.
So this is more about that final bit. Like you are in a region, you have arrived there, you get a request from customer. How do you know now in which cell is the customer located in?
Yeah.
And that part is based through Lambda. DNS based, you're absolutely right. They work well for the regional routing part. Right. Now, there is a little bit of like magic here, or rather lack of magic, because I said like one of the goals whenever you're building the cell-based architectures is you need to avoid having global state, but you can't quite avoid having all global state. So we have to kind of be a little bit pragmatic here, and we do have some global state. Okay, so but we have very little of it. We have a little bit of tenant per tenant information in a database, a DynamoDB database, which is it's a global one, so it's replicated around the world, okay? And this DynamoDB database is also stress tested for recovery. We have, backed it up. We do game days where we test its recoverability under failure. And more importantly, there's very little bit of state in the O of kilobytes of data. Whereas the cell itself has potentially could have petabytes of data in the DynamoDB that deals with like the non-tenant management part, all the other metadata, all the other things that we keep per tenant, like when was the last backup done, what kind of activity did we see there, was there ransomware, and things like that. Okay, so this is kind of like the pragmatic split here. The global state is not cellularized. There is really, if you can think of it as just like one cell, but that cell is, I shouldn't say cell because it's not really a cell, but that state is heavily replicated and heavily backed up as well. And we do disaster recovery exercises on those kilobytes of data. Okay, so this is where you do need a little bit of state, but most of the other one, the petabytes should really reside inside the cell. Okay. Now, this is something interesting because sometimes I fall about this myself. So what about data plane cells? In our world, the data plane, as I said, it's Fargate itself. So here we need to be really careful and I have some anti-patterns in the last section, which is like not to reinvent the wheel and take cells too far. Sometimes I need to remind myself of this as well. So the container service, Fargate itself, is already cellularized. Its control plane, and I have a link to that. There is a really nice video that describes that. Its control plane is already cellularized by AWS. So we get this for free. So we should kind of resist the temptation to, or S3 for that matter, we should kind of be mindful there that in our case, we didn't need to do anything about the data plane. It was, we got the cellularization for free. Okay. So only do the cellularization when it makes sense, when it's the services that you're kind of putting together that manage some state, and things like Lambda or Fargate or S3 or DynamoDB there, or from other cloud vendors. I'm sure they're already cellularized. I mean, double check, but you probably don't need to recellularize them. Yeah?
Can I
Main
ask
takeaways.
a Fargate
Yes.
question? I don't know if it's exactly your area of expertise, but one thing I was on the fence on is Fargate a good place for mission critical work? And it sounds like you think yes, it is, but was there any catches, gotcha around using Fargate for something that is supposed to be performant, highly available, all those things?
It really depends on the workload. For us, it works well, but again, the kind of workload we have is also. Let me just give some examples. Sometimes, we do backups, or we analyze the data that we have already backed up. We analyze it for ransomware. If Fargate if one of those tasks is ever down, like in one of the AZs, we simply restart it. It goes to another AZ, and our data plane, the course of it, implements something. I'm getting into the details, but I think that's important. Implement something called incremental backups. So you can always start off from where it left. So for us, Fargate is not say sending streaming data or data that we need to look at like all the time. Is doing this task that we ourselves kind of checkpoint, and therefore we work around any kind of limitations of Fargate by just whenever we restart tasks, they just start off from where they left. Now, I'm just saying that our particular workload is more tolerant of Fargate's peculiarities. Having said that, I don't think I've seen like I haven't seen any more downtime from Fargate than I've seen from other services. I mean, we have already been through 2 or 3 Lambda kind of downtimes. We have been through 1 or 2 Fargate downtimes, and the control plane and data plane are resistant to that. The data I have right now doesn't show like any greater downtime for Fargate. But again, I don't want to take this too far, but if I were to implement, I don't know, like Kafka or other services like that really are streaming data with Fargate, I'll probably think twice in those cases, right? Yeah. Because maybe there where you really need like the low latency and you really need it to be, you're looking at all the bytes, maybe that's not good enough. But no, this is just like a discussion, no big data to like prove or disprove that.
Yeah. Makes sense. Thank you.
Yeah. Cool. So what are some of the takeaways so far? Again, monitor quotas, build a thin routing layer. This will be a bit of work, and avoid the need for global state. And maybe 3, the cost of opening the new cell is tending to 0. There are services that unfortunately do not dial up and down as the usage goes up and down. I think they all promise that, but some of them are not there yet, okay? So a couple of practical tips to end with. The first one, tiny cells. This is kind of useful for like extreme isolation. Sometimes you might have a customer that needs to reside in a particular zone, maybe a government customer, or some customer that really must not reside with anybody else on that account. Yeah. So sure enough, you can open a cell, you can put the customer there. That's great. Right. The other reason you might need tiny cells is for testing. You can start with a very tiny cell and direct the first direct a new piece of software, deploy it to this tiny cell first, and route only 3 customers to this tiny cell. And that's great. Now, you got to be careful there, right? Maybe one of these customers is actually you. You're kind of like dog fooding your own food. Maybe because these 3 customers hopefully are not going to suffer a lot from like mistakes you make in your code. But the point here is that this helps with A/B testing. And if you do this carefully, it can really increase the overall reliability of the service. Question I always get is cell migration, because it's kind of exciting. I'm always asked, it's great, everything is great, cells are great, but if they get full, can we start to migrate the workload? I talked about when you seal the cell, when it's full of customers, and shall we migrate it? Shall we migrate that workload to another cell? And cell migration is hard. It's really hard. There's no magic there. There's going to be a lot of state. I tend to think of this is probably like a year 3, year 4 project in the startup. And yeah, it's hard. It's doable. Probably you'll have to do it like in the end. There's nothing that stops you. You can make use of services like S3 or DynamoDB or any other storage service. You have talked in the past about decoupling compute from storage, so you can make use of storage service to help you there. But I probably wouldn't start with cell migration. I'd probably make use of the fact that you can start a new cell quickly, seal the old one, and even if customers from the old one leave, I think that's okay for a while.
Yeah.
So if you want to move fast there, you don't need to implement migration right
and
away.
the really key for that is to keep the cost of a cell to near zero, because if cells are expensive, and it's very much architecture dependent, then you are trying to maximize the value of a cell. You'll probably not seal it early enough.
Yes.
You're not going to leave a lot of space for people in the cell to grow, which is super important.
Exactly. So this help one another. But yeah, year 3, year 4, if you're done early with everything else in your year 1 and year 2, then go for it. And then again, like, it's worth reflecting after all of this, do I really need cells for my service, right? And the way I argue about this is that I would design for cells from day one, because I think the cost is low. I don't think we talked here about anything extraordinary you need to do. And most likely, even for the state, most likely you're keeping the tenant state separate anyway, right? And then I would kind of take the pragmatic view where you design for it, you monitor the quotas, you monitor the customer load, and the startup starts adding some customers, right? And add the second cell whenever it's needed. Now, meanwhile, test that before you add the cell, obviously, right? But then don't add it if it's not needed, right? So if you're, if scale the effort as the number of customers enters the system, but design for cells from the beginning. That's the case I'd like to make here. And finally, an anti-pattern. Don't cellularize what's already cellularized. I alluded to this. Here is an example where there is some service where you're trying too hard to cellularize. You have potentially created, say, multiple Fargate clusters, and which is okay. But then I don't know what you've done. You think you might have cellularized it. You're calling like different endpoints, and then you have some complex routing, which is possibly a lot of fun, but probably unnecessary. And then you're calling Fargate in different ways, but Fargate or S3s or Lambdas control plane is already cellularized. So no matter which way you call it, it's going to go to a cell. And if the cell is down, another cell is going to take over on a retry. So don't cellularize things that are already cellularized. In summary, hopefully I convinced you that cells are needed to build even more robust services that we've had before, with the decoupling of the control plane, the data plane, and the availability zones. Those are great building blocks. We just added the third one to our shelf. We talked a little bit about what the cells are, routing, how you need to monitor them. We had a little bit of a glimpse into some of these, details. What does it really mean using Alcion's control plane, and some practical tips. Hopefully, I've shown you that cells in the past typically used for critical services. Today, hopefully, everybody can use them with a little bit of effort. Where you want to go from here? I've put some examples here. AWS Fargate under the hood, great talk. A lot of detail about how its control plane is built. Other case studies, DoorDash has a video on the journey to the cell-based microservices architecture, and Slack has a blog post about how they moved to a cellular architecture. That's it. Thank you.
Thank you, Eno. While we're on this slide, I just want to do a small plug because my former team at Confluent recently delivered a paper in VLDB, and it's around their core engine, which is kind of the way they resort Kafka. And it's one of those papers when they try to talk about 5,000 different things and only spend a few paragraphs on each. But one of the themes there is their move to cell-based architectures as well. So It's definitely something that is kind of trending.
Absolutely. I have not read the paper. I heard they won a best paper award of sorts.
Yeah. They're absolute rock stars. It's very bittersweet to see your former team being such rock stars in such a big way.
I should have added here. Please add it as a link as well. That paper is on my to-do list for reading it. I saw that they won the award, and I had no doubt that they would.
There will be a link in the show notes, as usual. So, I don't know if you want to leave the slides on for this part or not. Let's try without, and I'll bring the slides in if needed. So one of the things you said is that, hey, you can do cells on day zero, which I love. And you're right. Cell is basically what you would otherwise write and just deployed in a certain way. The part that actually looked hard, you also mentioned that you need a bit of a global state. And you mentioned how much you tested the global state to make, because it now becomes the critical path. This seems like possibly a heavy lift for early stage company.
It might be, and I'll add a little bit some stuff I didn't mention there. There is a little bit of global state, but if you want to go into the details even more, there is a little bit of code as well that's being deployed in these routing lambdas, and that's deployment as well, which is which you need to. What is that expression? Like, if you keep all the eggs in one basket, you better really watch that basket, right?
Yes.
So for us, the global state was not a heavy lift because naturally we wanted to keep some state for the tenants, right? Where we are doing data backup and they have strict requirements on where the data must be stored.
Yeah.
So we really already needed like a very simple mapping between, hey, there's the tenant, this is where the data needs to be, right? Once we had that mapping, we also realized that we were extra paranoid with it. We really want to replicate this, and naturally we started using like global tables, right? And then because we're extra paranoid, because we're a data protection company, we also want to do some disaster recovery. So we also tested that part really well. Now, in the end, it's just a DynamoDB table, which is global, that's backed up, and we've tested DR. Is that a heavy lift? I mean, I'm thinking about it. We certainly have to be mindful of it, but we had to probably do it either way. Whether we had cells or not, we needed this state. Now, we could have put it in all, in one big control plane, but it doesn't feel like a huge lift. I think maybe the routing lambda is a little bit more of a, when I look at our own efforts, it's a little bit more of a lift, to be honest.
Yeah, I was wondering a bit how much of the routing logic is something that actually API Gateway actually does. Like, you can tell it, look in that table in DynamoDB and give me my routing, or if it's something you need to implement a lot of.
There are many ways of doing this. This is the other thing. Depending on your service, there are many ways of doing this routing as well. And the routing itself is not complicated. It's very, very few lines of code. But the deployment there needs to be with no downtime. So if you're changing, if changing a little bit of code there, then the question is, how exactly do you test it? So that one was a little bit of heavy lifting.
Yeah, I'm trying to think if I have any more questions. And you mentioned something that was really interesting for me. You mentioned basically wanting to have zero cost for the new control plane cells, which meant that you went with a lot of lambdas and serverless things. One thing that I heard from a lot of companies who did a lot of work in Lambda was that it gets messy. And I was wondering if you had the same experience, that your sales logic got a bit messy, or if you had any techniques that you can share about how not to get into a mess.
Yeah, lambdas can, it takes a while to get used to them. I mean, certainly in terms of just developer productivity, not many developers are used to programming with lambdas. It's just a very different way of doing things. I think, and you'll be pleased to hear this, I think one of the ways we're kind of keeping the architecture simple is through the use of an event bus. So, there is going to be multiple times the case where you insert some state in your database, and then you want to fire off a whole bunch of lambdas depending on what the state was. And, we don't want it to be the case that you have like the lambdas all over the place, all trying to listen to this database, and it just becomes, it just becomes like a nightmare. So the use of the event bus, where you just put the events there from DynamoDB first, and then you fire off the lambdas, certainly has simplified things. That's number one. Number two, we've been really careful, and I think this is important, something I didn't talk about. We've been really careful that all the work that our lambdas do is idempotent. And that has been our main. Now, that's not easy. That definitely requires some thought. But the net effect is that all our lambdas are idempotent. So the moment, if they do fail, you can redrive them. And you can redrive them without worrying that, hey, something will go wrong with the redrive. We're going to get the data twice or 3 times. You redrive them, they're idempotent. You can rest assured that like a simple retry is going to solve your problem, right? So the use of the event bus or event buses and idempotence makes the situation slightly easier. Now, I've read friends who have looked into like deeper aspects of software engineering, and I'm sure there's a paper out there that says like, do you do it with the Lambda or do you do it like with like, like something else? And I'm not entirely sure like where the cutting edge is, certainly like in academia for this kind of work. But yeah, I think event buses and idempotence have gotten us quite far, and have gotten us really up to speed with like the speed of development and the speed of deployment is unbelievable.
Amazing.
Yeah.
That's all a startup really needs, right?
Yeah. Certainly at the beginning.
Yeah. Is there anything I should be asking and I'm forgetting? I'm now looking there.
One last thing about the costs, since you mentioned the costs and the routing. Our routing might be a little bit more complicated, but I also I don't want to leave the audience with the impression that all routing is complicated. There will be cases where doing like a simple, as you said, like with API Gateway, doing a simple hash of the tenant ID and you can find the cell, and there is like no concern with routing. Okay, it's just we cannot do it like that because of our particular peculiarities, but that's completely possible. Okay, you can consistently get into the cell that you want with a very simple calculation.
I do want to warn listeners.
Yes.
I've had to do the whole tenant routing thing.
That
I
doesn't
think
work
the
well.
first time since was in year 2000. So every once in a while I do it for the last 20 something years. I will do some hash function. It doesn't work after
a while.
Literally after the first time you deploy. If your launch is at all successful, you will need to add an extra cell. Do you actually want to move everyone around? No, you don't. You really don't. Because as you said, migrating tenants between cells is the hardest thing in the world. So whatever you do not do the hash function.
No, that's fair. I just didn't want to scare the audience. Like they don't always have to do like a complex like routing either.
I agree.
Hopefully, for their cases, sometimes the routing can be simpler. Maybe it's not as simple as the hash, but hopefully it doesn't have to be super complicated.
Yeah, I wouldn't like. There is like the consistent hashing that Cassandra talked about, again, it works in some cases, and exactly the cases where moving a tenant from cell to cell is no big deal.
Yes. Cool.
So, yeah.
Well,
Hey,
thank you for having me here. This has been really great.
Thank you so much. I learned so much, and it was just probably the clearest explanation of cells, especially for early stage companies, that I've ever heard. So thank you so much for it.
Thank you.